Hello, good evening, good morning, everyone. It is my pleasure today to welcome you to this new episode of the CALYM Institute Red Talk. Tonight, our focus will be given to advances in AI and pathology with a specific example from a collaborative research to the clinic. So I'm really happy today to welcome Charlotte Syrykh, hematopathologist from Toulouse University Hospital, Eliott BRION, data scientist at Owkin, Jean-Baptiste SCHIRATTI, lead research scientist and medical imaging co-lead at Owkin, and Mathilde BATESON, senior data scientist at Owkin. So tonight, Red Talk will be divided into two parts. The first one will be given by Dr. Syrykh, Brion, and SCHIRATTI to present the collaborative work they've done on the development of interpretable deep learning algorithm for microarrangement prediction on E-stained whole slide images. And it was focused on large B-cell lymphoma. And then Dr. Bateson will give us an overview on the recent advances in the AI-based tools in pathology and on Owkin's developed AI solution in digital pathology. I will first start by just giving a few words of introduction on the Carnot CALYM Institute, and then I will leave the floor to Mathilde Paradis to introduce our partner, Owkin. So Carnot CALYM Institute first is a Carnot Institute. So the Carnot label is granted by the French Ministry of Research to public research structures with proven competencies dedicated to fostering innovation through industrial partners, partnership. And the Carnot CALYM Institute is specifically dedicated to lymphoid research with 20 entities covering the whole value chain from discovery up to phase 4 steps. And we gather together 18 academic research teams, the international cooperative group LYSA, and the academic clinical research organization, the LYSARC. So thanks to these 20 entities, our objective is to make major discoveries on lymphoma, of course, and transform them into therapeutic innovation that will then move from innovation into drugs for the final benefit of patients. CALYM represents those expertises, but also resources such as biological resources, but also data coming from healthcare or clinical trials, and also biological material and technological platforms such as the Lymphoma Data Hub that will be used, which was used to perform the ILYA project, a public-private partnership that was funded by Carnot CALYM Institute and done in collaboration with a partner, Owkin. CALYM has a double objective, which is to support internal innovation and platform development, but also to support public-private partnership and ideally to combine both in projects such as the ILYA project that will be presented tonight. So I will now leave you with Mathilde Paradis for a brief overview of Owkin, and then we'll jump into science with the whole teams to present both projects that was introduced. Thank you very much and have a nice Red Talk tonight.
Well, thank you, Delphine, and hi to everyone. Well, I'm glad to introduce everyone to Owkin. Owkin is a tech bio using AI to find the right treatment for every patient. So we've been founded 7 years ago by nematologists, and we work with the multimodal data in multicentric research program. And so what we do is that we work actually with our worldwide partners of top academic institution in order to find the best data to run our projects, and so I'm happy to lead the floor to Dr. Syrykh to show to everyone so we can know more about the ILYA project. Thank you so much.
Okay, thank you, Mathilde, and good afternoon, everyone. I would like to thank the RedTalks organization for inviting us to present the ILYA project, being the result of a very fruitful collaboration between academic research and industry. So ILYA project is a French acronym for Lymphoma Imaging Through Artificial Intelligence and aimed at predicting MYC gene rearrangement from H&E stained slides of diffuse large B-cell lymphoma through deep learning models. So to start, a few words about the birth of the ILYA project, which began 2 years ago under the impulse of Professor Camille Laurent and Professor Christiane Copie-Bergman, who decided to exploit the broad databases of DLBCL patients included in the LYSA clinical trials, for which we had comprehensive clinical, radiological, pathological, and molecular data, in order to develop machine learning models able to process this massive data and discover potential genotype-phenotype correlations or biomarkers. So on the LYSA side, we were able to digitalize and annotate DLBCL pathological slides, which constituted a huge amount of preliminary work. However, we lacked expertise in artificial intelligence, and thanks to CALYM, the company Owkin has been approached and accepted to take part of this adventure. So now a few words to introduce large B-cell lymphoma, which remains the key topic of our presentation today. This is the most common type of non-Hodgkin lymphoma in adults. It's an aggressive and highly heterogeneous disease with about 70% of patients who will respond to standard R-CHOP immunochemotherapy, while the remaining 30% of patients will be refractory and will relapse quickly. Unfortunately, these poor prognosis patients cannot be identified at the time of diagnosis, and it is crucial to find some predictive biomarkers that could help to stratify patients, identifying those who could benefit from other more intensive or targeted first-line treatment. A well-known poor prognosis biomarker in DLBCL is MYC gene rearrangement, which is found in about 7 to 10% of cases. And this molecular abnormality is assessed through FISH techniques that are not available in all laboratories and represent an important workload. So herein is the algorithm of large B-cell lymphoma diagnosis presented in the last ICC classification of hematolymphoid neoplasms. As you can see, the diagnosis of DLBCL relies first on H&E examination that guides ancillary techniques such as immunohistochemistry, in-situ hybridization, and FISH analysis. The integration of all these results enables lymphomas to be classified into broad categories. And moreover, not yet in clinical practice, but we hope soon, genomic analysis allow DLBCL to be dismembered into molecular subgroups with specific biological background that might lead to personalized therapies. By learning from vast datasets of medical images, such as histological slides, machine learning algorithms can identify patterns that might be overlooked by the human eye, and thus can be trained to predict tumor classification, molecular data, and even clinical outcomes. So the objective of this study was to predict MYC rearrangement in DLBCL from H&E stained slides using innovative AI methodologies. I would like to stress out that this task cannot be performed by the pathologist's eye. So thank you for your attention. I will now let Jean-Baptiste SCHIRATTI continue the presentation, and I will see you back at the discussion section.
Thank you. So I will present the material and method section. The data that was used to train the model consists in 1,247 DLBCL patients in 4 different cohorts or 4 different groups of DLBCL patients. So the one with the most patients, so the GEDI cohort was the one that was used for model training. It consists of 565 patients. And the other 3 cohorts, so NH091B, RP3, and senior, were used for model evaluation. So on this GEDI cohort of more than 500 patients, we trained our model using a cross-validation scheme, meaning that the cohort was split in different parts. Some of the data was used for model training, and some was used for evaluating the model. And once we got a model that was good enough on this GEDI cohort, the 3 other cohorts were used as external validation. So this figure represents the workflow that we developed for the training and evaluation of our model. So it starts with whole slide images that are H&E stained, and then the first step that is applied, and it's a facultative one, is color normalization to make sure that the staining of all the whole slide images is more or less the same across whole slide images. And then we apply a tiling, meaning that we do two different things. So the first one is matter detection. So this is the black and white mask that appears on the upper left part of the second figure. So you can see that this mask represents the mask of detected matter on a whole slide image. And then the detected matter is split into non-overlapping patches, which are usually much smaller than the H&E image. So for this study, we decided to use 200 by 24 by 200 by 24 pixels patches, which is kind of a standard way of splitting whole slide images into patches. So as a result of tiling, the detected matter is split into patches, and then a whole slide image can be considered as a collection of small patches. Each of those patches are then given as input to a pre-trained model that we call feature extractor that will convert the patches into vectors or representations or embeddings. And to do this, we use the pre-trained model that is called PHYCON, that is a vision transformer based, trained on whole slide images from different therapeutic indications, so different types of cancer. And then this feature extraction step, will convert the patches into tabular data, basically vectors for each tile or each patch. So then as a result of feature extraction, a whole slide image can be summarized as a table with as many rows as patches and as many columns as dimensions output by the feature extractor. Then comes the model training, where we use a model called DeepMill to predict whether a patient was MYC positive or MYC negative, meaning whether or not the MYC gene was rearranged or not. And eventually, we can have a look at the attention layer of this DeepMill model, and we get an interpretable heat map, as you can see here on this figure, with cold and hot regions that will be discussed later. I just want to mention also that this feature extractor, so called PHYCON, has been open sourced recently by Owkin with a non-commercial license. And I will give the mic to Eliott to talk about the results.
So for the result, I propose to discuss first the result that we had on the cohort that we use for cross-validation, so the GEDAI cohort on the left, and then we'll discuss the external validation on the 3 remaining cohorts on the right. So what you have on the left are different work curves that shows on the bottom the specificity, which is among all the patients that are not MYC rearranged, what is the proportion that are correctly classified. And on the left, you have the sensitivity, which is among all patients that are MYC rearranged, what is the proportion of patients that are correctly classified. The algorithm outputs a number between 0 and 1, and when you play with different thresholds to define whether a patient is predicted rearranged or not, this yields the different curves that you observe. Each color corresponds to a different repeat. So actually on the GEDAI cohort, we didn't run the algorithm just once, but we did 3 different partitions on the cohort of GEDAI, and we measured the performance each time as defined by the area under the curve. So a random model would correspond to the dashed line, and this model would have an AUC of 0.5, and a perfect model would have an AUC of 1. What you observe is first that on the GEDAI cohort, the performance is better than a random model. And also, we observe that between the different repeats, you have more or less the same performances, with AUC ranging between 0.79 and 0.81. Let's now look at what it gives when we take this model trained on GEDAI and then infer it on the 3 remaining cohorts. So again, you have 3 curves, and each color corresponds to a different validation cohort. And what we observe is that although the performance is a bit under what we observed for GEDAI, which is expected because GEDAI is the cohort on which we chose the hyperparameters, we still see that we have relatively good performance with AUCs ranging between 0.62 and 0.75. So the algorithm output a number which measures the chance of a slice being microarranged, but this is quite abstract, and in clinical practice, it's interesting to know, to have more understanding about how the model took its decision. So to have more intuition about the interpretability, one way to do that is to look at heat maps. On the left, you have heat map for a case that was actually non-rearranged, and on the right, you have a case that was actually rearranged. So if you look at the case on the left, in the heat map, blue correspond to zones that the algorithm didn't take into account to make its decision, while red correspond to regions that the algorithm highly took into account to make its decision. On the top left, you also have the raw slide to have a visualization of what it looks like. And so if you look at the high attention zones, so for example, in A, B, and C, you also have those little tiles that are shown here corresponding to those regions. And you can see that they correspond to tumor region. And the opposite, if you look at the blue region in D, E, and F, they correspond to non-tumor region. If you look at the slide, which is microarranged, you have a similar behavior with red region corresponding to tumor tiles and blue region corresponding to non-tumor tiles. What this means is that in general, the algorithm looks at tumor tiles to make its decision while disregarding the tiles that does not compare tumor, which is the expected behavior. So in the preceding slide, we discussed the AUC, which is an interesting metric, which is independent of the threshold that is used. But in clinical practice, you want to know whether your sample is rearranged or not. And so you need to set a good threshold. So what is a good threshold? So in clinical practice, this would be used as a pre-screening tool, meaning that we want to identify microarranged patients with a very low number of false negatives. So in this setup, we would use the tool to make a MIC-R prediction. And if it is predicted as having a high chance to be MIC-R, then we ask for a FISH test for confirmation. In the case where it is predicted as being non-rearranged, then we stop there and we don't test further the patient. So we look at what it would look like on the senior cohort, which gave the best performance on validation with 0.75 AUC. And what we show here is confusion matrix for the threshold that we chose. So on the bottom, you have the label that is predicted by the algorithm. So 0 means that the algorithm thinks it is not microarranged, and 1 thinks that the algorithm thinks that it is a microarranged case. On the left, you have the true label, again, 0 being non-rearranged and 1 being rearranged. So if you look at all the cases that correspond to predicted label non-MIC, which is shown in red here, you can see that among those patients, for the chosen threshold, there is no patient that were actually a MIC case, meaning that the false negative rate is 0%. And on the left, you have the patients that were predicted to have a microarrangement, and you have some patients of them that actually had a microarrangement. What this means in practice is that you can avoid doing the FISH, which is both time-consuming and costly, for 35% of the case, without missing any patient that were actually microarranged. I will now leave you with Charlotte for the discussion.
So thank you, Eliott. And to sum up, we have developed a deep learning framework able to predict microarrangement in the LBCL from H&E with ROC AUC from 62.2 to 81.9%, depending on the cohort. One of the main strengths of this model is its interpretability through the attention score its maps, making reliable the predictions made by the algorithm. We also settled a promising pre-screening tool with high sensibility to limit laborious FISH techniques. And finally, some limits. First, the lack of true external validation due to the centralization of both preparation of digitalization of slides. Second, MYC rearrangement prediction, where irrespective of its partnering gene or other genetic alterations that might influence predictions. And finally, the pre-screening tool that remains a proof of concept and need to be generalized on independent cohorts. So to conclude, this was a successful collaboration to tackle medical challenges by leveraging large clinical databases and strong expertise in AI and pathology. So thank you all for attending our presentation, and we will be glad to answer your questions if you have any. So I will let 5 minutes for the potential questions, but if there are no further questions for now, we can come back to the question and answer session after the presentation of Mathilde BATESON. So we have some questions. The first one, can you detail the basis of criteria used by the algorithm? So maybe Jean-Baptiste or Eliott, it's a technical question. Do you mean the features maybe? I don't know. Basis of criteria?
Yes, I can take this one, but I'm not sure to fully understand basis of criteria. So what do you mean by this?
I was wondering maybe features, but I am not sure.
Yes, so depends also what we call algorithm. So because there are two different parts involved. There is the feature extraction step that is done using a pre-trained model, and there is also the deep mill part. So the deep mill model that is an aggregation model that was trained to predict the rearrangement status at the slide level. And so, yeah, can you please specify which part of the model that you're considering?
So black box, say like maybe we don't know which features are taken into account for the prediction. I guess this was the question. Yeah,
so can we learn on the findings, and is it black box? So yeah, so that's a good question. And so it's difficult actually to know what the input representations or the input feature correspond to, because this pre-trained model that we use is quite a deep model with millions of parameters. So we know that the representations, the values that are output by this model are useful for what we call downstream tasks. So if we want to predict patient prognosis, if we want to predict whether or not the patient contains some kind of specific mutation, those representations will be useful to do that, but it's difficult to make the link between those representations and something that we can see on the whole slide image. So in that sense, yes, those representations can be a bit black box, but the model deep mill that we apply on top of those representations is interpretable by design, as Eliott has shown.
Yes, so thanks to the interpretability, the heat maps.
Yeah, so thanks to the interpretability of the heat maps, we know which part of the image are actually relevant for the model prediction, and that gives us some kind of some kind of tangible information that we can then discuss with clinicians.
So we can move to the next question, which is the same remark. Were you able to identify anatomical features specific to the MYC hair cells beyond them being in the tumor cell area? So maybe I can take this one. So we looked at the slides that were predicted with MYC hair or non-hair. So as we used to see in pathology practice, there were some tendency of cases MIC-R to have more necrosis or to be more monotonous, but nothing 100%. It's when we have such a slide under the microscope, we can guess that maybe there is a chance it is MIC-R, but we are not very at ease with that. And it was the same with this algorithm, as we had the MIC-R and non-R established by fish, so nothing very obvious. So next question. Have you tried to correlate the features to genetic alterations depending on non-R versus R? So this one, I don't get it. Have you tried to correlate the features to genetic alterations? So I think it's the same question, no? Like morphological aspect that correlate with R or non-R, if I understand well. So I don't know if Eliott or Jean-Baptiste, you have a better idea. So we just looked at MIC-R, and we had double hit, triple hit, and simple hits, but we didn't look at other genetic alterations. So the next question. So in slide 10, was the analysis on MIC fish avoided based on all cohorts? No, or just the GDI dataset. So I think you mean the pre-screening tool. Yes, the 10. So maybe I can take this question. We just use the senior cohort for this analysis to settle the threshold and to assess the result. So that's why we say that it's a proof of concept and it needs to be confirmed over independent cohorts. So can we know the findings of this? Okay. Another question. On the heat map, one sees a border effect, blue color, artifact or fixation, or true results. Yes, it's a good question. When we go on the heat maps, we can see all around the sample the blue section. Maybe when we look at the tiles, we can see that most of these tiles are peritumoral tissue or artifact. So we think it's more non-tumoral tissue. Then, what is the structure of AI? Number of layers, number of nodes? So that's a question for Jean-Baptiste or Eliott.
Yes, I can take this one. So again, the model we trained is a model called DeepMill. So it's a model that has a specific architecture that is described in a paper published in 2018. If you want to have a look at it, I can give the link in the chat. So this model basically consists in 3 different parts, I would say. So the first one takes the different feature vectors as input and combines them into a condensed representation that can have an intrinsic dimension. So I think in our case, this intrinsic dimension was something around 64, if I recall correctly. So I would need to have a look at the paper. But so the idea is that we take the input representation that have dimension 768, and we start by reducing them to something that is much smaller. Then comes the second part of the DeepMill model that computes attention scores. So it's what we can see on the heat map. Some tiles, some patches have higher attention score than others. So that is the output of this attention layer. So it's a score between 0 and 1 that says basically how important this part of the whole slide image is, and then comes the third part of this DeepMill model that is what we call a multi-layer perceptron. So it's dense layers that will somehow transform again this condensed representation into the output of the model. And so in that case, it's just one value because we're dealing with a binary classification task.
Okay, thank you.
So I hope this answers your question.
I guess yes. So another question, can you compensate for overfitting in the training set? So this is for Eliott or Jean-Baptiste, I don't know who want to answer to this technical question.
Do you want me to take it, Eliott, or do you want to go ahead?
Yes, go ahead, Jean-Baptiste.
Okay, so overfitting is a known problem in machine learning. It can happen in with every machine learning problem. The bigger the model is, the more likely it is to overfit the training set. So we use different strategies to mitigate this overfitting effect. The first one was that, as I presented in the slide where the different cohorts were described, we have almost 10% of MIC-rearranged patients in each cohort. So that's basically 1 patient out of 10 is positive. Means that for 1 patient out of 10, the MIC gene is rearranged. So that's not a lot. So in that case, it's something that is likely to give overfitting. So we sampled the positive and non-positive cases evenly to make sure that whenever the model sees a batch of data, it would see as many positive patients as it would see negative patients. So sampling patients non-randomly and sampling them with different weights. I mean, we subsample the negative one and we oversample the positive ones is a strategy to mitigate this. Then during model training, there are also things that we implemented, such as dropout, regularization. So all these different techniques are ways we can actually mitigate overfitting. And then having external cohorts like LNH091B, RT3, or senior is a way to assess whether or not the model did overfit on the training data. And so if the performance on those validation cohorts is good, then we can confidently say that the model did not overfit.
Okay, thank you, Jean-Baptiste. So maybe the next one, I can take it. Are you satisfied with the AUC values for the different cohorts? Will an increase in cohort number increase the AUC number, or the model features could be considered to improve? So this question, thank you for this very interesting question, because it's a big point. When are we satisfied with the AUC in clinic? I would have said never, or when it's 100%. But that's why we decided to set up a kind of pre-screening tool with high sensibility in order not to miss fish rearranged cases. So that's so I think we are satisfied because it's better than 50%, and it's a task that we cannot do by ourselves from the H&E. I mean, so it's a good result because we can find some morphological data that suggest MIC rearrangement. But I think that this kind of tool has to be fine-tuned in order to be used in complementarity with fish techniques or molecular techniques in the case of a pre-screening tool, for example. And yes, if we increase the cohort number and the diversity of the cohorts, we expect the AUC number to be increased as well, but that's a guess. So I hope I answered the question. I don't know if Jean-Baptiste or Eliott has you have something to add to this.
That's good for me.
Okay, so next question. In the JEDI cohort, what proportion of fine needle biopsy and surgical biopsy samples? So thank you for this question. I can take it as well, as I just had a look. We had around 70% of resection and 30% of biopsy, and we carried out the analysis of comparing the prediction on biopsy and the resection, and there were no differences in terms of accuracy. I mean, so the algorithm worked well on both resection and core needle biopsies. So another question from Ellen Jaffe. What technique was used to identify MIC-R cases, and how do you rule out cryptic error? Did you use breaker parts? So yes, this is a very good question. Thank you very much, Ellen Jaffe, for this question. So we used the breaker part probes, only breaker part probes. So this is a limit of this study, I admit. We cannot rule out cryptic rearrangement, but in clinical practice, we don't use sequencing, for example, to assess MIC rearrangement. So this is a limit, but we use Visis breaker part fish to be more precise. And yes, this is a limit. We didn't use fusion probes with AGH, if it was the question. So how do you account it for class imbalance, if any, during algo training?
Yeah, I think Jean-Baptiste already referred to that. So actually, we sampled the positive and negative case evenly to make sure that even though one classes is more present in the dataset than the other, that the algorithm see the two the same amount of time.
Okay. So the size of the collected tissue we have already answered, and the kind of material as well. It was a question about core needle and resection, so we used both, and mostly resection. Another question. So is this AI approach applied on anatomical images been already published by other research teams, maybe for other diseases? If not, what are the closest applications you have seen? How would you apply AI for heterogeneous data, image, clinical, sec data, possible or not, as of today? Who wants to take this one?
I can take this one. So was this AI approach published? Yes. So it's been published in different parts. So the feature extraction part, so this FICON model has been published. So there is a preprint that is available on medRxiv, in which we explain how the model was pre-trained, which data was used. So we basically use data from 16 different TCGA cohorts. So it's a lot of data. So we give all these informations in the preprint on medRxiv. And the deep mill model is something that is not new. It's been around for some time now, and there's a publication dating back to 2018 that presents the model, its architecture. How would you apply AI for heterogeneous data? So that's a very good point. So in that case, we had images and clinical data. So as you've seen, images were the input, were used as input to the feature extraction step, and then to the deep mill model. The clinical data was used to define the model outcome, so whether or not patients were MIC rearranged. If we wanted to develop models on more heterogeneous data, so for instance, images plus tabular data plus sequencing data, such as, say, RNA-seq, then we would need to come up with an architecture that would be somehow more complex. So just to give you an idea, so there are different architectures that allow to learn from heterogeneous or multimodal data, but to the best of my knowledge, there is not a single one, or like there is not a given model architecture that will work for every task with multimodal data. So it's more or less a case-by-case problem where whenever you have heterogeneous data, you need to try different ideas to combine those different data modalities and to train to be able to train a model on top of these different data modalities. So very naively, what we could do is keep the same model, so keep this deep mill model, but compute embeddings. So for the tiles, for the images, we keep the clinical data as is, and we also compute embeddings for the RNA-seq data, and then we concatenate all those embeddings, and we give that as output to the deep mill model. So concatenating all the data is one way to do it. Obviously, there are more elaborate ways to do it, but there is not a one-fits-all rule to that. So I hope I answered the question.
Thank you, Jean-Baptiste. So 2 last questions. What is really interesting is that there were no false negative and false positive will be validated by FISH. Would be interesting to use other independent cohorts to check if false negative equals 0. So we fully agree with this remark. As we settled the threshold on one cohort and use the same cohort to validate, this is the main limit of our pre-screening tool. And yes, this is something to do to validate this usefulness of pre-screening tool for mid prediction. Senior is a cohort of patients age 80 or over. Are there any explanation for the better results observed in this cohort? So this we had no idea. Yes, patients were aged more than 80 in this cohort. But as the MIC rearranged cases were balanced between all the cohorts, we didn't know why it performed better than on RT3 and LNH 09B. I don't know, Jean-Baptiste or Eliott, if you had anything to add, but
no, I guess you answered it correctly. I think it's also a limitation of our approach. So it's difficult to know why it would perform better on other cohorts.
And about the age, another last question. Do you know if the Jedi cohorts were also older adults? Not the Jedi cohorts were all adults. More and less 60-year-olds. There were a mix of ages. Only the senior cohort were older patients. So I guess we are done with question and answer for this part. So now let's move to Mathilde Bateson presentation about recent advances in AI-based tools in pathology and the Owkin's developed AI solution that have started being used in the clinic. So thank you, Mathilde.
Hello, everyone. Thank you. So we'll start by a very brief overview of recent trends and advances in AI in pathology. So let's start by the status today of the challenges and limitations of AI in pathology. We can outline first poor data quality, so only a few data, low quality of data samples, etc. Unimodal data, so for instance, only imaging data or only clinical data, etc. Then biases in data. So for instance, this can happen if you only have data from one hospital, then it will be probably very difficult for you to create a model that can be robust in many hospitals and in all clinical settings. Finally, one other challenge in developing AI model for pathology is the lack of expertise altogether. It's very difficult to reunite experts in statistics, in AI, in pathology, and medical experts, so that you create a model that is both very effective, very robust, and also interpretable. And this leads me to the last point, which is that today a lot of AI models are still black box models, which is not reassuring for clinical adoption. So there is a lot of focus to be had on interpretability. So the way forward is having top quality data, multimodal data, as few biases as possible. Validate by experts all AI models that are being produced, and focus on interpretability. So one thing I would like to focus on is the multimodality, which we have already discussed in the first part. So it's a very challenging task, and there is a lot of ongoing research, and it's one of our very big focus at Owkin. So the challenge is, how can you centralize omics data, histology, radiology, clinical data into and use this in one AI model to uncover actionable biomarkers. So this is one of I guess the big trends. So once you have this very multimodal, very powerful data, then you can maybe start asking and tackling very interesting questions. So AI model can be used for different things. First, it can be used for, I guess, lower risk tasks, such as augmenting human experts with tumor detection, automatic tumor detection, automatic tumor grading, automatic cell classification. But then the second part, and it's one of our, I guess, our biggest focus at Owkin, is to go up the ladder of the risk and up the ladder maybe of also the possible benefits. So trying to predict mutation expression, mutation and protein expression, trying to predict response to treatment, and trying to predict, for instance, cancer outcomes. So we really think that this is only possible if you use multimodal data. So as a panorama of things that we have been developing at Owkin, biomarker model based on multimodal histology and molecular data. You see on the right table many Owkin models that have a different cancer indication. So breast for relapse risk, which is a tool that aims to predict post-treatment relapse for early breast cancer. And then colorectal and gastric cancer for MS-INTUIT, which aims to predict MSC status for checkpoint inhibitors and is CE marked, and etc. So I will now focus on the second model, so MS-INTUIT. So MS-INTUIT, it's the first AI solution for predicting micro instability for colorectal cancers directly from H&E slides. So microsatellite instability in colorectal cancer is an important biomarker. For instance, it has been shown that MSC patients show better prognosis and do not benefit from chemotherapy in stage 2. And it has also a therapeutic interest to know the MSI status, because ICA has been approved for MSI patients independently from the cancer types. However, MSI positive status only represent 15% of all colorectal population. So today, gold standard techniques have their limitations for testing MSI. There is an important workload. You have quite a lot of technical preparation. It increases the time to diagnosis. And finally, you also encounter inter-observer variability. So our motivation for developing MS Intuit is to try and detect the MSE cases that you can rule out. So for instance, what if you can identify the rule out for 40% of the patients and assess that their status is MSS. So this is what MS Intuit does. It produces a direct testing from digital H&E slides that predicts the MSI status with a very high 95% sensitivity and 99% NPV. And allows to have a lighter operational footprint in the pathologist routine. So how does it work? Is you take a tissue sample, you digitize the H&E slide, you pass the H&E slide into the MS Intuit model. So it's behind it is a deep neural network that extracts and analyzes features. And then a PDF report is generated assessing whether the patient is MSI or MSS. So in 40% of the case, it will say that the patient is MSS. So you can avoid additional testing. And in 66% of the time, it will say that the status is underdetermined. And here the recommendation is to go further with the gold standard technique. So now for the interesting part, how did we train MS Intuit? So in this part, you will see quite some similarities with Jean-Baptiste and Eliott's presentation in the first part. So here behind the MSI model, you have an AI algorithm that learns to predict the MSI status by training it on many H&E slides. So here, the pipeline is the same as in Jean-Baptiste's presentation. So you have a pre-processing step with tiling, and then you have the feature extraction, and then little by little, by training the AI model, it will learn to focus on the most extreme tiles, so the highest and the lowest. So these are the ones that correlate to the MSI status of the patient, and will issue the MSI likelihood score for the whole image. So again, MS Intuit colorectal algorithm leverages Owkin's histology pipeline. So you go from the H&E slide to an MSI probability using Owkin's feature extractor. So it's a pre-trained self-supervised model such as FICON, which was presented by Jean-Baptiste. And then you pass it through a downstream model, in this case, Schroeder. And you output an MSI probability. Okay, so moving on to the validation, and how did we validate the performance of MS Intuit? As I said, it's a very important part. So first, the model was trained using public data, so it was trained on TCGA data. And then to validate it, we used a blind validation using Medipass network. So it's the largest pathology network in France with more than 100 pathologists. 29 pathology labs, 14 technical platforms. And so what we did was we had access to 600 patients, which were scanned twice using 2 different scanners, Roche and Philips. And then a small part, so 30 patients, were used for calibration. So calibration is a step that allows to go from a score to a final prediction. And then the blind validation was done on the remaining patients, both for Roche and the Philips scanners. So what is interesting is that the performance is very similar on the 2 scanners. It's very high, so 80% AUC on both the scanner 1, so Roche, and the scanner 2, Philips, with quite similar sensitivity and NPV. So we can say that MS Intuit is robust on an external cohort on which the model was not trained on, and which has different data acquisition protocols. And then this is also the very reassuring part, is that comparing on the bottom plot, the x-axis represents the score for the first scanner, and the y-axis represents the score for the second scanner. So you see that you have very high agreement between the 2 scanners. So a slide that will be digitized by the first scanner and the second scanner will have a very high probability of having the same prediction status by our MS Intuit model. Finally, and importantly, there is an interpretability by design in the Owkin shoulder model, which means that results are as you see on the left, you have an attention map which shows which part of the slide is predicted with high probability of having MSI instability. And so here it's on the bottom in red, and on the top in blue, low prediction. And so by analyzing more precisely the content of the tiles, of the high and low scored tiles, we were able to connect it with the biology by saying that higher risk tiles show more poorly differentiated tumor and mucinous aspects, and also TILs, whereas blue tiles, so low-risk tiles, showed well to moderate differentiated tumor glands. So again, results are produced in an easy-to-use PDF format, so that the histopathology expert has access to both the score and the interpretation of the model. And then as a finishing slide, I guess as the title of the talk was from collaborative research to the clinic, I wanted to show also what the timeline looked like for the delivery and the development of MS Intuit. So in 2018 was the first proof of concept. In 2020 was the publication in Nature Communication. In 2021 was a presentation at Nikkei. And in May 2022, the CE mark was obtained. And then after presenting at ESMO, the poster in 2022, it was finally developed within the Medipath network in 2023. And today we are in 2024, so we are focusing on the V2 of MS Intuit, which I will now briefly summarize. So the version 1 of MS Intuit was focusing on only surgically resected tissue. So the main advance of the V2 will be to be able to predict the MSC status on both biopsy and surgically resected tissues. And of course, improve the rule-out percentage and also get a CE mark approval. And then for the V3 product will aim to extend the MSI prediction for other tumors that we believe are interesting to predict. So we are aiming for 3-4 new tumor types as this for this MS Intuit pan-tumor version. And this is my last slide. So thank you for your attention. And I will take your questions now.
Yes, thank you very much, Mathilde, for your presentation. So now we will answer the question. So the first one, how do you explain the difference of accuracy? 95% for colorectal cancer and 70% for DLBCL. So it's like a parallel with our previous studies. I think so.
Let me.
Why DLBCL? Because you obtained the high AUC, and
we are talking so 87% AUC.
Yes,
and we have a very high sensitivity performance for the MSI status. I mean, one answer is that maybe the task is a bit easier. The second answer might be that maybe it was trained on a lot of data. You know, not all tasks can be directly compared.
Okay.
I don't know if if Eliott or Jean-Baptiste want to add on for the discrepancy in performances, but when the task is very different.
Yeah, I think indeed the tasks are very different, so it's difficult to compare ROC AUC scores. Obviously, one is lower than the other, but we are basically comparing two different things on two different data sets with different models, so it's not really comparable. And also, I would like to mention that in light of using these tools in clinical routine, ROC AUC should not be the target here. So I think it's a good measure to measure the performance of a model. So for instance, by doing cross-validation and something like this, but the real metric that we can be interested in is sensitivity or negative predicted value, because in the end, what we actually want to know is can we rely on this kind of model to do pre-screening or not? And that's not really what the AUC is telling us. So AUC is a good metric, I would say, for data scientists, but keeping in mind that we want to apply the model in clinical routine, we should have a look at other metrics such as sensitivity or negative predictive value.
Yes, so thank you for this answer. So next question, same strategy as the previous study, you eliminate negative patients and send the undetermined to standard tests. So is that a specific strategy of yours, or can AI be expected to also accurately stratify and eventually in a non-binary decisions? So I guess you have already answered. So in the two study, yes, we use the pre-screening tool, but I let you answer, Mathilde.
So you can eliminate.
It's a better model question.
Yeah, this is. I think this strategy makes a lot of sense as a pre-screening tool, and as a first adoption of a tool to the clinic. But of course, if it were possible to have a final binary decision, which would not require any further human expert, then why not? But yeah, I guess I can also add that I think one of the things that is also behind your question is for the model to know when it's not sure. It's an important part of AI adoption to the clinic, is also for the model to say, okay, in this situation, maybe the data is of poor quality, maybe I won't answer on this patient. I need a further review by an expert.
Okay, so we are waiting a few minutes in order to see if anyone has any further question. So once again, thank you all for your interactive participation in this high-tech and futuristic RedTalk conference about AI. Have a nice evening and see you soon. Yeah, some question, sorry.
Yes.
Sorry. Final word on how you see the field evolving.
Okay, so I will have a go at the first answer. Maybe my colleagues can complete. What I can say is that we are focusing a lot at Owkin on the things that I have been talking about. So model robustness, model uncertainty quantification, and a lot of also on model representation. So this is the first part. This is for instance, the FICON model that Jean-Baptiste just put in the link. So one of the things that we think is very important is to have a very rich and very powerful representation. So AI representation of the slides of the or of the data as a model agnostic, task agnostic representation, because this kind of is a way to address the low amount of samples that we have for each task. So if we have one very powerful representation model that is task agnostic, then you can use it for the DLBCL project or for the MS Intuit project. And so this is one of the things that we are focusing on. Maybe if my colleagues want to add something on how we see the field evolving.
Yes, maybe I can add something on the pathology side. In my sense, this kind of tool could help pathologists in the diagnosis, such as immunohistochemistry and molecular data analysis had done before. I'm not sure it will replace anything yet, but I think we should use them if when they will be in clinical practice. It could be a help, like assistant of the pathologist for us. I don't know if Jean-Baptiste and Eliott, you want to add something?
No, I think it's a good point, and Mathilde also gave a good answer. So, in my opinion, I think that pre-trained models that have been pre-trained on lots and lots and lots of data will be more and more important. So people are starting to call those models foundation models. I know and I see that the field of foundation model for digital pathology is a competitive one. There are multiple groups, either from academia or industrial partners, that are developing their own foundation models. So we have our own model, so the FICON model that has been open source, but now we are starting to see more and more foundation models for pathology. Some of them which are very good, even better than FICON. So for instance, Microsoft and PageAI did their own foundation model that was trained on millions, or I think it was 1 million whole slide images. So it's something that is huge, and we can expect those models to disrupt the field of AI for digital pathology. So yeah, my prediction is that those models, either open source or not, will play an important role in the future.
And maybe there was another question, just to understand a bit more, are the number of features for colorectal and DLBCL the same?
Yes. So the number of features after feature extraction. So you have the slide, you cut the slide in tiles, and then you do a feature extraction step, which is, in a way, it's kind of a dimensionality reduction step. For the goal is to have a rich representation, but that is not too wide. And so the number of features is more or less the same in all of our projects after the feature extraction step. So a few thousands, between 1,000, 2,000, something like this. So yeah, so the number of features is not going to be the reason for the discrepancy in performance. I think our main response to the discrepancy in performance is the discrepancy in the difficulty of the task.
Okay.
Yes. So the DLBCL feature extraction step will produce something which will produce more or less the same number of features than the CRC feature extraction step.
So I guess we are done. No more questions. So now I can conclude. So thank you very much to all for this interactive participation, and see you soon during the next Red Talk.
Thank you. Thanks a lot.
Thank you.
Thank you very much. Bye.
Bye.
Bye.